Hello, this is Glenn Broderick from Vitrek, and today we're going to take a look at the PA900 series of power analyzers. This includes the PA910 and the PA920 as well. So this is a 4-slot device. You can put 1 to 4 cards in the back. Typically the best thing to do is pick the card for your application, and that tells you whether you need a PA900 or 910 or a 920. Now, I've got the channels 1 through 3 are connected to a variable frequency drive. We're going to take a look at that today. Channel 4 is the input to the drive. 1 to 3 are the outputs. And I'm going to, the first thing you do when you set up for a test, you come into the measurement config, and you can turn your channels on and off right here. And the other thing is come into the measurement mode, and for normal simple test you just put on a single VPA. Think of VPA as like group. It's one group. You only need one group. But we're going to do efficiency measurements today, so I'm going to use 2 groups, and I'm going to tell it to sync those 2 groups so that they're in phase when it makes the measurements. Now, over here under config VPA, I config VPA 1 as an example. And in VPA 1, I've got my channels 1 through 3. Again, that's the output of the variable frequency drive. And in VPA 2, I've got just channel 4, and that's my input to the variable frequency drive. So what I like to do is come in here and set up each of the different channels. Right now I've got it on low range. I've got my measurement period to 0.3 seconds. I can go faster or go slower. And this is a good compromise between response speed and resolution. I can lock on to the fundamental. This is an important setting on the PA900 because we base the calculations based on what is the fundamental. And so I've told it to use the current, lock onto the current, and that I'm going to be operating below 75 hertz so that it sees the proper signal, locks onto it. Bandwidth right now is unfiltered. Harmonics I've got set to the full 500. I can go, you know, some people want 25 or 50 harmonics. A lot of times I work with 100. Today, 500 harmonics, okay? The data is, coupling is AC and DC, just like an oscilloscope. The oscilloscope input. Response I've got on slowest. I like slow because the digits on the display move slower and I can interpret more of those digits. I find that more useful. I've got all 6 digits of the meter turned on. And over here I'm going to tell it how to combine. So for instance, on the wiring it says, are those independent phases or is this a 3-phase system? If it's a 3-phase system, is it a 3-wire or a 4-wire system? I'm going to tell it I've got a 4-wire system. Okay. So that's how you do the setup. And I come over to the power data, and right now we're going to take a look at channel 4. That's our input into the variable frequency drive. Just standard line power, 60 hertz, 121 in. The volt-amp reactive is negative. That means I'm driving an inductive load. The power factor is, 1 is the best. This is 0.31, so it's not very good, but typical for a complex piece of electronics. This is 3.3 watts we're drawing in idle mode. We haven't turned on the motor yet. That's why everything's so quiet. It's going to get noisy in a second. We're drawing 10.6 volt amps apparent power. Okay, so that is the basic measurements. Now the other thing I can do is I can come over here to the VPA 1, and now nothing there. Let's turn on my motor, and then this is the frequency that the variable frequency drive is putting out right now, and same measurement parameters. But I can now turn on basic as well, and in detailed, I can take a look at not only the power total coming out of the variable frequency drive, but how much of that is due to phase A or phase B or phase C. Now, if you look down below, you'll see that in addition to breaking the voltage up, we also have the phase angle. For instance, the phase between phase B and A is 120, that's leading,
and I'm sorry, lagging, and then the phase angle between C and A is 120 leading. So a lot of different data that you can get out of this. That's just the basic power data that we present. And from there, I want to take a look at the vectors. Notice that we've got 3 phases, A, B, and C. I'm triggering on channel phase A at 0 degrees. And again, this confirms B is at 120 degrees lagging, and C is 120 degrees leading. As I change the frequency, notice that it's, well, yeah, look at that phase shift right there. Notice that I'm reporting the phase angle with 1/100th of a degree, actually 1,000th of a degree resolution. So you can see the phases changing relative to each other as I'm adjusting that drive. Now, that is the vectors. I'm going to go next into the oscilloscope. The oscilloscope is a 12-channel oscilloscope, and it is capable of 22 or 24 bits resolution, which is really good for seeing small signals on top of bigger signals. Right now, I've got all the even channels set to show current, and there is the 3 phases of power that you would expect to see as I run it up in frequency. You can watch it change. I'm going to go a little slower on the time base so that I can see a little more of that. Okay, and so I can also come in here on the traces, put on the odd channels, and that's the voltage. And there you see the modulation. I can take it out of continuous and do a single shot. By the way, the PA900 is always recording data. We're just going to display it differently when we do things here, but it always has everything recorded, and you never have to do a test twice because the data is always in there. Now, I'm going to take that time base and make it faster. And you can see the different signals in there. Let's see. You can watch it adjusting. I can bring a cursor out here and look at any particular point. I can see that at the peak, I'm at 317 volts on phase C. And 120 volts on phase A. So that is looking at, by the way, I can turn on all of it simultaneously. No need to double probe, because when we set this up to do all of our measurements, basically the probes for that oscilloscope are already there and ready to make their measurements. Okay, so that is the oscilloscope mode, and so I can put volts, amps, and watts of any of the phases I want on there. By the way, I said this is a 4-channel device. I can actually get multiple units and connect them via Ethernet and synchronize all the sampling and all the start and stop and measurements. And I can turn this into a 12-channel system, possibly more. If you need more, just tell us, we'll figure it out. This is the history. As I've been playing around, I've been recording I can put volts, amps, or watts up to 4 traces over time onto here, and this is what it's been doing over time. And in the same way, The interesting thing about this, again, I can pull this out and put it wherever I want for making measurements, but the interesting thing about this is that the X scale dynamically rescales. So if it's a 10-second test, you'll have 10 seconds across this. If it's a 10-hour test, you'll have 10 hours across this. If it's 10 weeks, you'll have 10 weeks across this. So we can run very long tests. A lot of power analyzers run out of data after, say 90 minutes. We can run very long-term tests with this power analyzer. Okay? So that's the history. There is a spectrum analyzer in here. I'm not going to show it to you, but I will show you the harmonics analyzer. How's that? So this is, I can put in amps, volts, or watts. I can also look at the interphase voltage harmonics. Since I have 3 channels grouped as a, that is the harmonics between the phases. We'll give you an example. Now, you see that little yellow cursor. When I move that out, I'm slewing this up right there. It's about the 160th harmonic, and I can, for fine control, move it up and down and look at each specific harmonic. So you can see harmonic 161's at 14.75% of the power, and 167's at 20.89 as an example. So that's the phase-to-phase. I can look at it as amps, and the interesting thing, you can see the data changing as I run this up and down. Each one of these has a little different picture, different harmonics. Now, we can also set limits in here. Like, let's say you're testing the EM61000. That has limits at each specific frequency as to how high you can be for your emissions. We can use EM61000, but we can also put in custom limits. And so if you're testing your device and you want to check the custom limits, you can do that here. The last thing to show you was power efficiency. And so I have set everything into groups. I've got channel 1, 2, 3, and 4. You know about VPA 1 and 2. But then the last thing I can look at is efficiency here. So what we're doing is we're looking at the 110 in, and then we're comparing that to the 3-phase, 200 volts out. And we're showing an efficiency of about 85%. We have 35 watts going into the variable frequency drive. We have 30 watts coming out of it. We're losing about 5 watts. And so we're operating at about 86% efficiency at this frequency. Now, as I change the frequency, my efficiency will be different at different frequencies. Okay? So that's about it. I wanted to do this as quick as we could today to give you an overview of how to use the PA900 for 3-phase power analysis and for measuring efficiency. Thank you for sitting in on this. If you have any questions, feel free to contact us, and we have applications engineers ready to help you with your specific requirement. Thank you very much. Bye.